I times mi minus 1 minus mi. Right? That I can do. So, ich glaube, ich brauche noch 5 Minuten. So, what you effectively have now is you come to this formula, and as we did before for coming from the ripple carry adder to the serial adder, you can split this formula. Yeah? So what do we actually have now? We have now a sum over such terms, and we split it. What does this help us? Well, we can now collect not only 2 of these terms, but several of these terms. Collecting several of these terms means before we passed 2 bits at a time. Now we pass 3 bits at a time. Namely, or let me see, yes, M0, M1, M2. In the next step, M2, M3, M4. No, it's 4 bits at a time, sorry. M minus 1, M0, M1, M2. In the next step, with 1 overlap, M2, M3, M4, and M5. In the next step, with 1 bit overlap, M5, M6, M7, M8. So we put 3 bit at a time into our computation, and we are still correct. What we need to do is we need to multiply now with different powers of 2. So, and that we compute in different radix. So before we had overlap of 1, and we had 2 power of 0, 2 power of 1, 2 power of 2, 2 power of 3. Now we have here in the inner sum 2 power of 0, 2 power of 1, 2 power of 2. That is what we can parse. And in the outer sum, we have 2 power of 0, 2 power of 3, 2 power of 6. So we are effectively powers of 8, right? So this here is 0, 8, 8 square, 8 power of 4, and so on, right? So in that way, we can try to get more efficient. Now, what we need to do is we need to put other parser rules in place. The other parser rules look like that. So this is our bit sequence. For this individual bit sequence, the same applies as before for this boost algorithm. So we take 2 bit. If this is 0, 0 or 1, 1, we add 0. If it's 1, 0, then we add 1. If it's 0, 1, then we subtract 1. What we subtract? The corresponding power of 2. So if here is a 1, 0, we need to add 2 to the power of 0 times 1. If we subtract here, we have, this is on the second position, so 2 power of 1 times minus 1. So we need to subtract minus 1. Here we have a positive, so we need to add 2. So we effectively, in this, if we see this sequence, we need to add 1 times this term. Here we need to add 2 times, and so on. At the same time, the rule says these are powers of 8. Powers of 8 means instead of shift by 1, shift by 3. So we shift now by 3, and the overall rules look like here. We have here to add R. We have here to add 2R, 3R, 4R, and here we have then correspondingly to shift always by 3 afterwards. And that gives us another algorithm. And we can do this actually with an arbitrary power of 2. We can do this with an arbitrary shift. And we will result in different rules here. what is the problem if I increase here the number of bits I process at the same time? What is harder to calculate? Well, you still need only an adder and subtractor, but what you need to do is you need to pre-compute here additional values. Yeah? And pre-computing additional values from a certain point on doesn't make sense, because, well, what you want to do is a multiplication. Why to do another multiplication beforehand? So this limits the effectiveness of this algorithm a little bit, so that you usually only take size of 2 or 3, or 3 or 4 bits that you process at the same time. So you operate, in other words, in radix 4 or radix 8. But if you operate, for instance, in radix 4, then, well, your pre-computation becomes very simple. You need to be able to add r, 2r, minus 2r, and minus r. Minus r is just 2's complement. Minus 2r and plus 2r is just a shift of the number or of the 2's complement. So that's easy to pre-compute. We can just do this on the fly. Hardly any overhead. So that makes definitely sense. And you process in each clock cycle twice the number of bits if you go from 2 to 4. 3 times the number of bits if you go from 1 to, or 2 bits at a time to 4 bits at a time. So if you go from 2 bits at a time processed to 3 bits at a time processed, you effectively halve the number of steps you need to do overall multiplication, which gives significant speed up, even in the worst case. In the best case, you're even better. Okay, the algorithm for that then looks like this. I don't go further in detail here, and that's enough for today, I think. No? Good, so then I think we make, what, 10 minutes, 15 minutes? Yeah, so maybe till 10:50 a break, and then we continue with the exercise, and we see us tomorrow.
Where do you get the 0 from here? The 0? How do you know is it?
All right, so I would say we continue with the tutorials. So first thing, I would pass on the signature list. Please sign it. So usually I start tutorials with a short recap about what we have done during the last session. So let's quickly get into that. There were some confusion about the questions about the research diary. I shortly wanted to clarify these things. So everything regarding the research diary, so the additional credits you get, all the information you find on the lecture slides. So this is the information you should refer to if you have questions regarding the research diary. So, and what this all is just like a offer from me. So because for your research diary, you need to ask questions and you also need to answer them. And this is my offer to provide you with answers. So during the last tutorial session, I offer you to answer your questions you haven't been able to answer by yourself or by asking your peers. So this is like the additional offer. And in order to be able to give you a very good answer, so a not like not prepared answer, I would suggest that you send me an email until May 23rd with this question, so I can prepare to answer them. This is just like an additional offer for you so that you can write an answer in the research diary. Is that clear now? Yeah, perfect. All right, then let's have a short recap what we did yesterday. We talked about FPGAs. A short introduction of what FPGAs are, field programmable gate arrays, and the benefit of them that they have configurable hardware. So the logic functionality that is implemented on them can be changed after fabrication. They consist of lookup tables, flip-flops, and so on. In the field of hardware, FPGAs are kind of the middle ground. They are a trade-off between flexibility and performance compared to CPUs and ASICs. They have a fixed number of resources for logic, memories. So you need to think about what FPGA do you want to use? Is it suitable for the task you want to implement? A FPGA consists of CLBs, and CLB itself consists of two slices that contain LUTs, flip-flops, carry chains. Additionally, you can find on FPGAs so-called DSPs, PLLs, transceivers, and DRAM. There are two different types of slices, and if we look at lookup tables, then on our example FPGA, you usually find 6 input, 2 output LUTs, and you either can use all the 6 inputs to provide 1 output, or you can use just 5 inputs and provide 2 outputs. Then on an FPGA, you also find storing elements, so flip-flops, which are sensitive to the rising clock edge, and store the data if they see a rising clock edge. Then there are multiplexers, which select which line to forward to the output. If the select is 0, the first signal is forwarded. If select is 1, the second one is forwarded. Short example for a implementation of a logic functionality using a lookup table. So very important here, if you have seen Carnot maps before, it looks very similar. It also works very similar, but the main difference is that the encoding of the X and Y axis are not gray encoded. So be aware of that. And yeah, so very simple approach most of the time is like first to draw a logic table that realizes the functionality, and then you can think about, okay, what might be a good idea, and then you'll come to the result and then store like the logic table inside the lookup table and realize its functionality. There are two types of slices, as I mentioned before, slice L and slice M. Slice L is a subset of slice M. Slice M has additional functionality. M stands for memory slice, so the lookup tables can also be used as LUT, RAM, so as storage, and the flip-flops can also be used as shift registers. A CLB consists either of two slices L or a slice L and a slice M. So this slide is more about the indexing of the slices, and the naming happens like that column A is only on slice level and the row level on CLB level. The CLBs are connected to the routing network via switch boxes. And how do you actually realize such a hardware on the FPGA? So what you do is like you realize your functionality by writing code. So you use a hardware description language for that and write a RTL description of your functionality. Then you synthesize this written code, so your RTL retrieve a netlist which is a list of the modules that are contained on the FPGA and how they are connected. And then the next step is like to take this list and actually allocate resources on the FPGA and see whether there are enough resources, how you need to handle the restrictions of those resources, and find a way to implement that actually then on the FPGA. And during implementation, you then convert this to a bit stream, and this bit stream is the configuration of the FPGA, which you load onto it and realize the functionality you want on the FPGA. So then we had a short introduction to VHDL. I would skip over that for now because this is just like to see how this could work and look like. And most importantly, to take away from that is that you model a circuit and not a sequential process. So really think about modeling a circuit when writing your VHDL code. So it's not a program that happens completely sequential. It can happen also concurrently. Which language you choose is more or less a question of like which flavor you want to have, but in the end, the resulting circuit is independent of the language you use. All right, and then we went through some application example, which consists of all the modules you will see during the lecture and during the tutorials. And it can be used to have like a feedback loop for a UART implementation where the receiving data is just forwarded and send out the module again. All right, and afterwards we went through some examples of how to realize functionalities in lookup tables. This was the last example we had a look at. All right, so I think we haven't had any time yesterday to discuss this result. Are there any questions from your side regarding the last question of yesterday? No? All right. Then I have just like prepared an additional one for you. You don't find this one on the task sheet, so just a short recap. Try to figure out the function this LUT is giving you. So you have like 2 minutes, should be enough for doing that.
So I understand that if we want to standardize everything, usually you would start with we start with a 0, then 1, then 1, 2, and 3. But for here it says that it's x1, x0. So if it's possible, could I write it like, for example, like this? It doesn't really matter that much.
It doesn't matter. Okay. So it's exactly the same thing, and I don't care the order of it. So as long as it is the same.
Okay.
Yeah.
Thank you.
All right. All right, so there's the solution. So think about building blocks of ones, and one block is definitely this large one here, and then you'll find the first one, and the ref like, okay, you see the output is 1 if x0, x1 is 0, 1. And then you'll see a second block of ones, which is this one. And then you think about, okay, what is the condition there? And you'll see that x1 needs to be 0, and x2, x3 needs to be 1, 0. And then you will have a 1 at the output. And the resulting function then is like not x0, x1, or not x1, x2, not x3. I think I also got a question yesterday, what would happen if, for example, instead of a 0 here, there would be a 1. Could I reuse this one for building a block that goes like this, and another block that goes like this, if this is a 1? And you can definitely do that and reuse this one for both blocks. That's not an issue. All right, then I think I already did that today, but maybe someone is willing to answer this question for everyone. Just raise your hand and tell us the basic elements that are contained in an FPGA. Yeah, that's true. So the basic elements are LUTs, flip-flops, mugs, and carry chains. So if you have already the solutions open from yesterday, then yeah, that was an easy task. So these elements are grouped together in so-called slices, and 2 slices can be found in one CLB. And they are connected to each other with the routing resources or the routing matrix. There are also special elements like BRAM and DSP structures. They can be accessed via the routing resources and used for building up the functionality. Okay, this was everything about the first session, about lookup tables, how FPGAs are built. And next topic we're gonna discuss are like different memory types. And the first question is, what types of memories do you remember? So please name also some properties you remember of those memory types. You get for that like, yeah, I already heard DRAM, that's correct. I would say spend like 3 minutes on it, and then we will continue. Mm-hmm. Yeah, those are properties, and they are correct. So. Yeah. All right, I would say we continue and see what the solution is. So there are basically 3 different types: SRAM, DRAM, and ROM. So let's start with the first one, SRAM. So SRAM consists of 2 cross-coupled inverters. So they have a static load and typically consists of 6 transistors. And you also need additional sense amplifiers to read out the data contained. And they are very useful, especially for small on-chip random access memory, which is very fast. And typically you find that, for example, in caches. Then the second memory type is DRAM, so dynamic random access memory. It is very dense, so you have only 1 transistor and 1 capacitor. So the area you need to store 1 bit is very small. You also need additional sense amplifiers to read out the data. And since this is like very dense memory, you get large arrays of cells and get large amount also of storage then. Usually they are not on-chip like SRAM is, but they are off-chip, a separate chip that is connected to the processing chip, to the SoC via a bus interface. And this makes it also a lot slower than SRAM. So this is a bit the downside of it. And the other thing is like that it is non-static, it is dynamic. So if you do not refresh the data that is stored on this DRAM memory cells, you just lose them, right? So usually you have DRAM controllers that control those cells and also do automatically refresh them. And this is also like another bottleneck which makes them very slow or slower than SRAM, because if you currently do a refresh of a memory cell, you cannot access them or you cannot access another cell, right? So this makes them also slower than SRAM. And then there's read-only memory. So as the name suggests, you can only read the data, you can only modify it once, so it's only one time programmable, and afterwards the data stored inside is fixed. And how do you realize random read-only memory on FPGAs? Because FPGAs only contain SRAM most of the time. You just initialize it RAM once and only read it. Then you kind of have also read-only memory. So it's not true read-only, but you just use this as it was read-only memory. Then the second question is about NOR-based latches. So please answer the second question and draw a NOR latch. Explain how to reach the forbidden states, what the alternative would be to circumvent those drawbacks of the NOR latches. And if you have any questions, please just raise your hand and I will come and answer them. All right, I would say we come to the solutions, and maybe we start first with an inverter, right? So what we want is first an inverter. So does anyone know how an inverter is built using CMOS technology? Have you heard of CMOS before? Yes, all right. So what is the simplest way to draw an inverter? It consists of two transistors. One is a PMOS transistor, the other one an NMOS transistor. Here you have your input, and here you get your output. On this side you have VDD, and on this VSS. So this is like a very simple inverter, and if you think about it, if you have a 0 here, what happens? The PMOS will open and you have a connection to VDD, so this one will get a 1. If you have a 1 here, the PMOS will close and the NMOS is going to open, and you have a connection to VSS, so you get a 0 on the output. So that's a very simple inverter. And now we come to a very basic storage element that you'll find in digital circuits. You just need 2 of those inverters. So we're going to draw another one. And then what you do, you just like cross-couple them. So this means that one of the output is connected to the input of the other inverter, and the output of the other one again connected to the input of the first one. So now what happens? If you have a 0 on that side, you get a 1 on this side, and if you have then a 1 also on that side, you get a 0 here, and then you just like store this value, right? But for now it's like hard to change that value, hard to access it, hard to read it, right? So the next step is like, how do we come from a storage element to an element that can actually like store values, we can change them, that we can reset or set them. So for that we just use, for example, a NOR gate. And if we have a look at the logic table of a NOR, then let's call them A and B. So as long as you have a 1 in it, the output should be 0. And if there's no 1, the output is 1, right? And now the interesting thing here is, as long as A is 0, you see that you have an inverter. So the NOR gate can be used as an inverter in the case A is 0. And if A is 1, we set the output always to 0, independent of what B is. So independent of the stored value, as long as A is 1, the output then is 0. So now we have the ability to actually set values, right? So now we come from this one, exchange all the inverters with NOR gates, and now if we look at this one, if we look at the set input, so if A then corresponds to S, we can set a value which is 0, and 0 is like Q naught then. And if we do the same thing on the R side, we reset the value, and Q actually becomes 0. So, so maybe now we are going to have a look at how the different inputs correspond to storing, changing values. And as long as R and S are both zeros, we store the value, right? So if there was a 0 here, or then there is a 1 here, then this always is like our inverted chain, right? Because if if R and S, so A is 0, we get our inverters, and we just store the value that was there before. So let's have a look at how setting works. So we set then the NOR gate to the input to the lower NOR gate, so S to 1. So this means then that the output gets 0, and a 0 here corresponds to a 1 here, since here we have a 0 which enables the inverting, so then we get a 1 here. So now the output Q is 1. This is the reason why it's called set. Then we can have a look at the reset. So if we want a 0 on the output, we set R to 1, we get 0 on the Q side. Now S is 0, we enable the inverter, and we get a 1 on Q naught. And there are also like states you should not do, right? So what happens if you set R and S both to 1? Then you would set and reset your NOR latch simultaneously, which is something that should definitely be avoided, because then you have, in both cases, a 0. And why is that a forbidden state? Because what happens if you would afterwards now switch to 0 again, so say, okay, now we want to store the forbidden state, what would happen then? Then we have a 0 here, the inverter is enabled, so actually we want to have a 1 then here, but currently there's a 0, and a 0 here means we switch here to a 1, but there's a 0, and so on, so we just like get into a oscillating state there then. What is also important to know, especially for NOR-based latches, is that they are sensitive to logic 1, to the logic value 1. So now if we answer the second part of the question, how do we can overcome those problems? Any ideas? So what could we use instead of a NOR latch? A D flip-flop, definitely true. So we could use a flip-flop, a D flip-flop, a JK flip-flop, or a master-slave JK flip-flop. They both have the benefit, or they all have the benefit, that they don't have forbidden states. Any questions so far? No. All right. Then we come to the third question. How does a NAND-based ledge look like compared to a NOR-based one? Yeah, kind of inverted. Yeah. So I give you another like 1 minute, 2 minutes to draw it. All right. I hope everyone has a NAND-based ledge already. And it looks like this one. So the important difference here is that it is now sensitive to logic 0, meaning, so you usually depict this as not S and not R, so meaning that if here is a 0, then we have to reset, and if here is a 0, then we have to set, instead of a 1. So this is the main difference here. So now we come to the fourth question. What is the difference between latches and flip-flops? Right, I have the feeling that you already have some notes regarding latches and flip-flops. So what is the main difference? Anyone who wants to answer? Yes? Yes? So latches are level triggered and flip-flops are edge triggered. One thing. Something else? Yes. So latches have forbidden states, flip-flops do not. Okay. So this is like a short recap. So one point is still missing, meaning that latches can oscillate and flip-flops have metastability. So I guess you've all heard already about metastability. Yes? Anyone who wants to explain it?
Whole time.
Okay. So maybe we can also think about metastability from a little bit a different way. So meaning like, let's have a look again about the basic building block of a flip-flop, which is nothing else than a cross-coupled inverter. So this is really the basic building block. And if you then have a look at like the input and output voltages, so this is like V in, V out. Then usually you get like curves that look something like this. So meaning for a low V in, you get a high V out, and meaning for a high V in, you get a low V out. So this is like it would actually look like if you have a look at it from a physical perspective, and from a digital point, you only work in like the working areas of your inverter. So which is like either below here or below or above here. So usually if you have a flip-flop, you either have a V in that is here, then you get a defined V out that is here, or you have a V in that is very high, then you get a V out that is very low. So this is like how a typical inverter works, right? What happens if we add now a second one? So let me shortly think about that. So what happens if we now do this cross-coupling? Then this is V in for the second, and this is V out for the second. And we get a curve that looks something like this, right? So now as long as we drive these two inverters or use them as intended, then either we are here jumping to here, and from here jumping to here, and so on. And so this is like a very stable thing usually. And what happens now if we sample like in a wrong point in time? Then we would not have a V in that is here or here, but maybe we have a V in that is, for example, here. So at this point, then we would get a V out that is here. A V out from here means that we get a V in that is here. Then we go down here. And we see, okay, now we are in a very good range again and end up here and so on. So this then is like very stable again. But what happens if we happen to not like sample slightly left of this point, but exactly at this point? Then it's like we kind of stuck here, right? But as soon as we shift slightly to the left or to the right, we end up again here, meaning that we jump to here and here again, which like gets us in a stable state again. But if we end up at this point, we're like very comparable to on the top of a hill. So you could compare a metastable state as well like something like a hill. And if we happen to sample exactly at this point in the middle, then you end up here, right? And as long as there's nothing like disturbing this, you just stay there. But that would be in an ideal world. Since we are not in an ideal world, it's like environmental influences. At some point in time, you would slightly left to the left or to the right, and then you end up either in this direction or in that direction. But you don't know in which direction it is going, right? So this is what metastability can be explained like. Any questions regarding that? Okay. Then we have like 10 minutes left to maybe shortly introduce us to the next topic, which is timing of digital circuit. Hold time is already a buzzword that was said today, so this is what the next topic is gonna be about. And this is like the first task we want to have a look at. And so we now make a switch to sequential logic. We now have flip-flops as registers, and we have multiple register stages behind each other. And between those register stages, we have combinatorial logic. And now the first thing is we can have a look at is what is the functionality, so the logic functions that are realized in this case here. So what is the logic function for G, H, and I? And then we can think about, okay, how much time is needed for a signal to come from here to here? And why is that important? This is important because if we think about flip-flops and registers, they come with hold and set time constraints. And in order to fulfill them, it is important to know how much time it is necessary for a signal to travel from one register state to the other. Because if the time is too short, it might violate hold time constraints, or if it is too long, it might violate setup constraints. And I would say for today, we start with question A. And maybe we can also manage to do the B. But first, for the next 3 to 4 minutes, please answer question A. All right. I would say we come to the solution. I guess it's not hopefully too difficult. So how would be a good approach to do that? just go from the right side to the left side and follow the path, see which gates are all part of it, and then come to the function. So I highlighted now the path for G. So meaning you see, okay, we have here A and B. This is this gate, and this gate is C and D. And then both of those gates are ORed together to form G, which is nothing else than AB or CD. All right. The next one is H. So the same thing for H. So again, two ends for CD and EF, but now we don't have a OR for those two gates, but we have a XOR. And this gate here is a NAND gate, so we have here a NOT, so CD XOR NOT EF. And the third one is then I, very simple, just the NAND gate, so NOT E and F. All right, so then the next question is to calculate the propagation delays. So below the picture, you find like numbers which are for the propagation delays of the according gates. So for an AND gate and for the OR gate, you get 0.6 nanoseconds, and for the NAND gate, you get 0.4 nanoseconds. And the XOR has 1.2. So just look what gates are in that path and sum them up. So an example for TG would be that we have the AND and the OR gate. Why is there only one AND gate? Because those two happen in parallel, so you don't have the propagation here, right? Because the longest path here is just this one, and it's exactly as long as this one, so it doesn't matter which one you choose. They are both exactly the same, but important here is that you only use one, and this is why there's only one AND gate. So for H, which is the path for H? So now here the question is like, okay, you have this path here, and you have this path. Now the question is this one longer, or is this one longer, right? So one idea to do that is you calculate the one for the other and then the one for the other path and compare the results. Or you think about, okay, in what gates do they differ, which is this one and this one. Think about, okay, which one has the larger propagation delay. It's the AND, right? So we just use this path here and calculate the time for TAND and TXOR and come to 1.8 nanoseconds. For TI, it's very simple, just one gate, so 0.4 nanoseconds. And now the question is like, what is the propagation delay of our complete logic here? So of G, H, and I. And you just choose the one that is the largest, which is TH in our case. So this is the critical path. Questions? Yeah?
Why does it matter? Just an example.
It is just an example, but in theory it's like actually like that. Usually NAND gates are a little bit